You've got to guess the theme tune and the film. The winner gets a chocolate biscuit. Anyway, see if you can guess the film. Today's video is on factor safety. We have done it a bit in class, but just to give you a bit of backup. Safety factor or factor of safety, whatever you want to call it. And what it really is like we discussed, is ultimate stress over working stress. So it's a measure of how strong something is. So a factor of safety of 2 just means it's twice as strong. So the formula is ultimate stress over the working stress, and the ultimate stress is just the force or the stress is going to break at, stress at which failure will occur. That can be compressive stress, shear stress, or bending stress. That'll be a number. Every material's got a number measured in pascals. You'll normally be given it. So it's a figure that you don't want to get near to, because at that figure it's going to fail. The working stress is just stress is force over area. So it's the stress we've been working out. It's the recommended working stress, the stress that we recommend that whatever we're doing works at. Hopefully it's got to be less than the ultimate, because we don't want this working stress to be anywhere near really the ultimate. So normally you get given the ultimate stress and you've got to work out the working stress or work out the safety factor. Pascal are the units. So here's our example, nice and easy to begin with. Calculate the safety factor of a steel beam if the beam's material has an ultimate tensile stress. So it's in tension, and it's going to break in tension at 550 megapascal. And we're saying don't go any more than 360. So it's working, sorry, the ultimate is 550 and its working is 360. So it's looking good because that number there is bigger than that number. So our safety factor is going to be alright. So to work out the safety factor, is the ultimate over the working, that's the ultimate, and that's our working stress. And we get 1.5. So 1.5 is above 1, so it's safe to work at. So you can either do it like this, 550 to the 6 divided by 360 to the 6, press equals, press that, 1.5. Or because they're both in mega, you can just get rid of that and get rid of that, because they cancel out, and just do 550 divided by 360 and you get 1.5. So 1.5, so it's over number 1, it's over 1, so it is safe to work at. So lovely jubbly. Get rid of that, come down. Now 1 is very similar to the one that you'll have in your 6-week or some assignment, is this one. So we've got a 16mm diameter bar. It's got a length of 600. Don't forget to convert these into meters soon. It's being pulled apart, it's in tension by a force of 55 kilonewtons. Don't forget the killer, that means 1,000. The Young's modulus is 200 gigapascals. So we're given that. We're going to work out stress, strain, change in length is being pulled apart, so the change in length, and the factor of safety if the ultimate tensile stress is 600. So it's going to break at that, so hopefully our stress is going to be less than that. So the first thing we'll do is work out stress. We know that stress is force over area, we know that. We know the force, it's 55 and the area is a round bar, so pi r squared, or you can do pi d squared over 4. Don't forget, everything's in meters, so I've got 16 millimeters there. To get radius, divided by 2 to get 8, and then divided by 1,000, so 8 millimeters divided by 8 millimeters divided by 1,000 gives me 8 times 10 to the minus 3. 8 times 10 to the minus 3. It's 8 millimeters in a meter. We'll square that and we'll multiply it by pi, and you get plus E and G 201. So 201 10 to the minus 6 meters squared. That's our area. You can use pi d squared over 4, get the same answer. I probably recommend that you do use pi d squared over 4. It saves you having to divide something by 2. So that's our stress. So stress now is going to be force over area. That's our force from the question. That's the area. So 55 to the power 3 equals, don't forget the k, divided by 201 minus 6 equals, nothing wrong with that big number, nothing wrong with that. Press E and G, there we are, 273.63 megapascals. So you could put big M for mega. So 273 megapascals. Now, it's always looking good because that 273 is well below that 600, so our safety factor is looking good. Next one, strain. Now we haven't got a change in length yet, so we've got to use this formula here. Young's modulus, E is stress divided by strain. E is stress over strain. We need to find the strain. We know E and we know stress. So rearrange that formula, bring the strain up and bring the E back down. So strain is stress over Young's modulus. We know the stress, it's there. And we know the Young's modulus because it's in the question. There. So we know Young's modulus and we know stress. So that divided by that will give us strain. It's going to be a small number, no units. So 273.63 to the power 6. Or divided by 200. Giga is 9. Okay, 1.3, 1.37. So that's our strain, always small. The next one, change in length. So we know this formula. We know strain is change in length over original length. We need to find change in length. So I've rearranged that. I've just brought the original length up. So we've got change in length is strain times original. So I've rearranged that and I've got change in length is strain times original length, which is 600 from the question. I've done it two ways. That's my strain. I've converted the 600 millimeters into a meter there. So that times by that. 1.37 minus 3 times by 0.6 gives me 822 to the minus 6 meters, which is the same as that really. Because if I do this, if I do 0.822 to the minus 3, the same thing. So that's my strain, that's my length in meters, so that's my change in length. 822 times 10 to the minus 6 meters. I've done it this way here as well. I've kept it in millimeters. So I've kept it in millimeters, so it comes out in millimeters. So 1.37 minus 3 times by 600 millimeters gives me 0.82 of a mil. I can picture 0.82 to a mil better perhaps than I can that. So 0.8 of a millimeter, change in length, not much. We wouldn't expect it to stretch much. That's my strain. Last one, factor safety, if the ultimate stress is 600. So don't forget, factor safety is the ultimate over working. So that's the ultimate there, and this is our working stress there. So the factor safety is just ultimate over working. That's my ultimate and that's my working. So we've got 600, that way from 600 to the 6, all divide by 273.63 to the 6, all gives me 2.1, so 2.2 look. So it's over 2, so it's safe. Okay, it's safe. Obviously you haven't got to put they cancel out, so we could have just done this. 600 divided by 273.63 gives you 2.2. So saves you putting that in. So that's factor safety. Like I say, it's in your assignments. And just a little video to show you what happens if you don't take into account factor safety, because things do happen when you get to the breaking point. And this is what can happen.